This is part 2 of our discussion of the gas laws. We want to first quickly look at Amonton's law. This is also known as Gay-Lussac's law. It studies the pressure as a function of temperature at a constant volume and number of moles. And when we do that, we see that as temperature increases, pressure rises, and it is a straight line relationship. Pressure divided by what temperature is a constant? Well, the answer is, of course, absolute temperature or Kelvin temperatures. And the expression of this that we generally use in problem solving is P1 over T1 equals P2 over T2. Always express the temperature in kelvins, and remember there's no degree marking with the Kelvin K. This leads us to the ideal gas equation. Boyle's law relates volume directly to the reciprocal of pressure. Charles' law relates volume directly with absolute temperature, and of course with the usual constants. Avogadro's law relates volume to the number of moles at constant pressure and temperature, and therefore we can put those all together and we get the volume is directly proportional to the number of moles times the absolute temperature divided by the pressure. That means that the volume is equal to a constant times the number of moles and the Kelvin temperature divided by the pressure. And we call this constant R, capital R, and that's called the gas constant. This gives us the formula that we are familiar with. Pressure times volume is equal to the number of moles times the gas law constant times the absolute temperature. Now, what is the numerical value of the gas law constant? Well, we know that the conditions of 0 degrees and 1 atmosphere are called standard temperature and pressure, or standard conditions. Experiment shows that at STP, 1 mole of an ideal gas occupies 22.414 liters. If we plug these numbers into the Pavnert equation and solve for R, when we solve for R, it's PV over NT. If we plug the 1 atmosphere, 22.414 liters, 1 mole, and 273.15 K into the equation, we get a gas law constant when we're using atmospheres to measure pressure of 0.082057 liter atmospheres per mole Kelvin, and if we're using kilopascal, it's 8.314 liters kilopascals per mole Kelvin. Now remember, the liter kilopascal is a joule, so sometimes you see joules as the numerator of that constant. So if we solve a problem, the volume in liters occupied by 49.8 grams of HCl gas at STP, we use Pavnert, solve for V. We have the temperature and the pressure. We then solve for N. It's 49.8 grams divided by the molar mass of HCl, 36.45 grams. It's 1.37 moles. We could have just plugged this directly into the equation. And so when we take the number of moles, the gas law constant, the temperature, and the pressure, and plug that into our solved for V Pavnert, everything falls out except liters, and we get 30.6 liters. Or you could have just multiplied the 1.37 moles you got here by 22.4 liters per mole, because we are at STP. That is the shortcut, and there's no reason not to take the shortcut. Here's another practice problem. You might want to read it and then solve it with the video off, and then come back and check your work. Here's our Pavnert. N, V, and R are constant. Oh, that makes things rather easy, doesn't it? So what we have now with this constant is pressure divided by absolute temperature, which of course is Amonton's law. P1 over T1 equals P2 over T2. So when we solve for P2 and plug in the numbers, we get 140 kPa times 358 over 291. Kelvins cancel out, and we get 172 kPa solved for the Edison bulb. This is a patent filed in 1923 for a gas density apparatus. So we can find molar masses from gas density. We already know that. We start with Avogadro's hypothesis. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. This gave us, we've seen in another video, our table of molecular and atomic masses. We did this by getting the mass of a given volume of a gas and the mass of the same volume of another gas. At the same temperature and pressure, Avogadro tells us that the relative mass of the total is the same as the relative mass of the particles, that is, the relative mass of the molecules. So, if we define oxygen's mass as 32, which is what they did in the 19th century, then the mass of a molecule of methane, which if you take the whole volume of the two gases and measure them, we find out the relative mass of the methane is half that of oxygen. Therefore, 1/2 of 32 is 16, so the molar mass of methane is 16. A mole is then the number of atoms that gives the periodic table mass of any given element. This is all review. Density calculations. We know that the mass of the gas in grams and the molar mass is related to the density by the equations you see here. The molar mass of a gaseous substance, then, if you have the density and the temperature and pressure, you simply multiply density by the gas constant and the absolute temperature and then divide by the pressure, and that gives you the molar mass. This is an equation that many people have memorized. Now we go to gas stoichiometry because we are able to figure out volume for molar mass and temperature and pressure and vice versa. So we ask, what is the volume of carbon dioxide produced at 310.15 Kelvin in 1 atmosphere when 5.6 grams of hexene are burned? Here's your balanced chemical equation. We can go from grams of hexene, which we're given, to moles of hexene. Then, using the balanced chemical equation here, we can go to moles of carbon dioxide, and using the Pavnert relationship, we can go to volume of carbon dioxide. We do that here. 5.6 grams of the hexene, we multiply by the reciprocal of its molar mass, and then we go to the equation and see there's 6 moles of carbon dioxide produced per mole of hexene burned. Everything drops out except the carbon dioxide moles, 0.407 moles of carbon dioxide. Now, of course, we can go from that to the volume using nRT over P. We plug in our numbers for moles, the gas constant, the temperature in Kelvin, and the 1 atmosphere pressure. Notice we use the gas constant for measuring in atmospheres, and the answer, after we cross out everything except liters, is 10.4 liters. This leads now to Dalton's law of partial pressures. If you take two gases, as you see here, one with a pressure 1 and the other with a pressure 2, and you combine them in the same volume at the same pressure, as you can see, total pressure outside, you see that the two molecules are adding up their pressures. The volume and temperature are constant, and so there will be a higher pressure, as measured on the gauge, equal to the total pressure of the two gases. The partial pressures add up to be the total pressure. How is that? Well, if we define mole fraction as the ratio of moles of one component of gases to the total moles in a mixture, we see that mole fraction 1 is equal to the number of moles of the first substance divided by the total number of moles N1 plus N2 plus N3, however many there are in the mixture. If we consider a case in which two gases, A and B, are in that container, and they're in that same volume that the individuals had, we see that the pressure of gas A is found by the Pavnert relationship, where Na is the number of moles of A, and the pressure of B is found by the same relationship using the number of moles of B instead. Now we know that the total pressure then is going to be the pressure of A plus the pressure of B. Well, X of A is equal to the number of moles of A divided by the total number of moles, Na plus Nb. That's the mole fraction of A. The mole fraction of B is the number of moles of B divided by the total number of moles in the mixture. Once we have seen that, it takes very little thought to realize that the pressure of A is the mole fraction of A times the total pressure, and the pressure of B is the mole fraction of B times the total pressure. Therefore, for any gas that's in a mixture, its pressure is equal to its mole fraction times the total pressure in this container. So if we look at this question, this problem, go ahead and write that down and solve it. Turn the video off and then come back and look at the solution. The pressure of any component is equal to the mole fraction of the component times the total pressure. The total pressure here is 1.37 atmospheres. The mole fraction of propane, if you simply look, we've got the moles, is 0.116 divided by the total number of moles, which we added up. That would be 0.0132. That's the mole fraction. Therefore, the pressure of the propane is the mole fraction times the total pressure, 1.37 atmospheres, or 0.0181 atmospheres. Very simple type of problem to do. Now, the most common application of Dalton's law of partial pressures is getting the pressure of a gas that you've collected over water. If you run a stream of gas through water into a collection bottle, it'll be saturated with water vapor. Therefore, the total pressure of the gases in the bottle is the pressure of the collected gas plus the pressure of the water vapor. This is a diagram of what we just did on a potassium chlorate manganese dioxide reaction. You can see here, we heated it, we ran oxygen gas that's produced through water into the bottle. There's the reaction. Total pressure is the sum of the two partial pressures. You then go to a table of water vapor pressures, often given in millimeters of mercury, but you can find them given in kilopascal as well. The temperature determines the water vapor pressure. If you graph that, you'll see it's not a straight line. You can go to Gas Laws Part 3, the other video that's available.